Hello. Looks like there's two people in the meeting. Can you hear me? It seems like there's two people here. Bruno, do you hear me? People are joining. Can you guys hear me? I don't hear anything.
Yes.
Hello?
Oh, hello. Do you see the desktop? Can you hear me?
Yes, both.
Oh. Okay, great.
Yes.
There's about half the people here so far, so people are joining. Okay. You should see my desktop. This is the parallel programming class. We're going to meet this way for the first few weeks, and hopefully after a couple of weeks that we can go back to being in the classroom. Okay. Still people joining. There's still people entering the class, the meeting. Okay. I'm going to record this meeting so that afterward, I'll put the meeting up on the course website. I'll put the recording up on the course website after we're done. Okay. Let's see. Okay. Okay. Yep. Seems like about half people are here. All right. So this is the course website. First, let me just start off by talking a little bit about the website and how the course is going to work for a while. Okay. So everything you're going to need for the course is on the website. Brightspace is only going to be used for turning in homework assignments. So there isn't going to be any of the course material or anything on Brightspace. All the announcements for the course, all the reading material, the homework assignments, they'll be here on this website, and you'll use Brightspace just for turning in your homework assignment. It has got a reasonably good tool for submitting homework assignments. On this website, there's a syllabus, but I haven't finished it yet. So the syllabus isn't up there yet. Okay, I'll get it done a little bit right after class. I was working on the code for class today, most of the day, and I didn't get a chance to finish the syllabus. So the course is going to be based on homework assignments, and the homework assignments will be on this page here. The first one's not ready yet either. So your first programming assignment will be up here in a few days, and you're going to be writing parallel programming code, mostly in Java, and the course will be basically mainly about just doing programming assignments in Java, doing parallel programming. Okay, the main part of the website is this page here, which lists what we do each day. Okay, so there'll be an entry in this page for every day giving you, well, there's a link to this link was the link to the meeting. After class, I'll replace this with a link to the lecture. So after the lecture has been recorded and uploaded to YouTube, I'll put a link to the lecture up here. Okay, so every day there'll be an entry like this. It'll include your reading assignments, code examples we're going to look at. Like today, we're going to look at this code example. Okay, so we're going to start the course off by talking about threads. Threads are kind of like the basic building block of parallel programming. So we'll start with an introduction to threads. This overlaps with the introductory material is going to be coming from an operating systems textbook, because quite often threads are discussed in an operating systems class. So here's two different reading assignments, one from this online operating systems book and another one from this online operating systems book. Okay, so this reading assignment here is a short chapter on what concurrency means. Concurrency is another word for parallelism. Concurrency and parallel have similar meanings. Okay, so this is about threads. Okay, and it's actually, notice it's like chapter 26 of an operating systems book. It's threads, parallel programming and threading follow understanding basics of processes in operating systems. So the main prerequisite for this is to understand what a process is in an operating system. And then if you aren't a little bit rusty with that, you can go to this textbook's website, and there are chapters. See, there's chapters on processes. Here's the introduction to what a process is. And here's another chapter on coding processes. So that's the basic. We'll say a little bit about that as we go along, but processes are the building block for. We're under here's where the threads are. We're not going to do all this stuff in this book. We're just going to use this introduction to threads because we're going to switch. This is done in C. We're going to switch to using Java. So it's much easier to explain what a thread is using C than it is using Java. And then after we get a sense of what a thread is and get a basic understanding of what a thread is using C, we can switch over to Java. Java is an easier language to use than C is, but it's a little bit harder to explain what threads are in Java because Java kind of conflates object-oriented programming with threading in a kind of not great way, in kind of an awkward way. So when you try to figure out what a thread is in Java, it can get real mixed up with what an object is. So we'll stick to C, which is real simple. It makes it simple to understand, makes it simpler to understand what a thread is. Okay. And same with this, there's 2 introductory chapters on threads from this book. Then there's this short chapter. This is more about the code. The first chapter is more about the idea. This one's more about the code. See, they talk about the thread API, the functions you call for doing thread coding. Okay. And then this other book has a chapter on threads. This one's kind of interesting. The chapter is both on C threads and Java threads. So it introduces C threads and it introduces Java threads at the same time. So it's a good reading assignment because it helps go from the C style threads, like here's a Java thread program and here's a C thread program. So he's got examples, a simple multi-thread program in C and a simple multi-threaded program in Java. So we'll start with the C versions, and then in another, and maybe next, I'm not sure if this week, probably next week, we'll start with the Java versions. We'll start looking at Java code for threads. Okay, so your reading assignment are these 2 introductory chapters on threads from 2 operating systems textbooks. Okay. And then I have a bunch of code examples in this zip file here. So just click on it and then download it. Okay. And it downloaded to my desktop. Well, it's slowly downloading to my desktop. Most of what we do in class is going to be looking at code. So almost every day we'll be downloading examples of code and running them and talking about what the code does. Okay, so if I unzip this folder, okay, there's a bunch of code in here. And it's C function, C programs that we're going to look at. Okay, and there's also some of the references I linked to on the website are also in here. So for example, here's the chapter. See, there's that chapter on threads from the book that discusses both threads and Java threads and C threads. So I put a link to it in here. This is another introduction to threads. This is from a book that it's not a free book. It's a book you have to pay for, but the university has a site license for it. So for example, if you double click on this link here, the university has a subscription to this thing called Springer Link that lets us download textbooks from this publisher. Okay, so like right now I'm not logged into the university's. If you're on campus, instead of saying buy this ebook, you'll be able to download this book. And the chapter on threads is this chapter here. And you could download the book, or you could if you're on campus, you can download the book. Now I put it actually in that zip file. Not the book, I put the chapter on threads. There's the chapter on threads. It's already been downloaded into the zip file. But if you're interested in the book, the university paid some kind of, through the library, we've paid some sort of subscription fee that gives us access to all the textbooks from this publisher called Springer Verlag. And they publish a lot of really good computer science textbooks. So this is an example of one of their books that if you go to their to the link for the book on the Springer Link website, you can just download the book. Okay. Now you need to be on, you need to be on campus to do that. Okay, if you're at home, you probably can't download the book from home. But if you're anywhere if you're on the campus network and you log into any computer on the campus network and you go to this website, so if you follow this link, if you double click on this link from on campus, when it opens that website, instead of saying buy this book, you'll see download this book, and then you'll also be able to download individual chapters. Okay, so you don't have to download the whole book. This is a pretty good book on parallel programming. But it's geared towards traditional parallel programming has been geared towards scientific computing, and it's mostly needed by people doing high performance scientific computing. But that's been changing in the last few years. Right now, a huge part of parallel programming is big data. This book is a little bit more old-fashioned. This book is basically about the high-performance scientific style of parallel programming. We're going to probably lean more in the direction of trying to understand how big data systems are set up. So we're going to approach parallel programming more from the more modern point of view. It's not really more modern. It's just the point of view that now where parallel systems are being used to analyze large amounts of data. That didn't exist even like a few years ago. Parallel programming has existed for many, many years, but it was almost always used for high performance scientific computing. So all the examples would be, let's write programs to solve partial differential equations, or let's write programs to multiply large numbers of matrices. So all the examples had to do with scientific computing. And this book's like that. Most of the examples come from scientific computing. But now you're starting to find, and there's not that many textbooks that do this yet. Unfortunately, the stuff is going faster than textbooks can keep up with. But for the most part, when people now really use parallel programming, like Google and Amazon, Google's not solving PDEs, Google's analyzing data. And most people now are using parallel programming to do things like that, to mostly process large amounts of data and analyze data. So that's what we'll try to kind of lean towards, is that style of parallel programming. And that's where Java gets used. The high performance parallel programming people were almost all writing in C and C++. So all the textbooks out there on parallel programming, almost all of them are C books. But the modern big data people are mostly programming in Java. And they're using Java frameworks like Spark, MapReduce, fork join. So they're using these different libraries than the high performance people use. The high performance people use C and C+ libraries that do mostly numerical computing as fast as possible. And the modern modern data people are using libraries that just process mostly text. A lot of it, they're not doing numeric stuff. They're processing text files, large amounts of data, trying to find stuff in data files. Okay, right. So in this zip file, if you download it, there's a couple of the references are in the zip file here, and then there's all this code. Now I want to start talking about the code, but before we can, if it's C code, you have to be able to compile it. So up on this website, I put a little baby compiler that I've been using for courses. This is a simple little compiler that I use like in the classroom, or I give it to students. It was set up for the operating systems course. If you click on this zip file and download it, that zip file includes a C compiler. So let me, now it's really done. There's something wrong with the campus network. It was like this yesterday. The campus network is incredibly slow. Okay, go ahead and download that zip file if you can. I already have it on my computer, so I'll show you what it looks like. After you download it, you should unzip it like I unzipped this zip file here. Then copy the unzipped zip file to your C folder. See, I already done it here. Copy it to there. It needs to be on your C drive. It won't work if you put it anywhere else. It's a simple little compiler, and to keep things simple, it requires that you put it in one place. You need to put it on your C drive, right under. It should be unzipped right under your C drive. Actually, unzip it anywhere you want, but then copy it to your C drive. Then if you open the folder, okay, this is the folder that holds the compiler. This is the GCC compiler that's used on Linux. So what I did is I took a port of GCC to Windows and built a little compiler around it. Okay, so the compiler is down in here. There's the compiler. So if I open a command window here, and I type GCC -- version, I see that it's the GCC 4.5.1 compiler. Okay, so it's the same compiler. It's an older version of it. Like this is a fairly old version of the GCC compiler, but it works fine for us. We don't need the latest and greatest version of the GCC compiler. Okay, so this will be our compiler that we use. And what's nice is this compiler is the same compiler that comes with Linux. So we could also use Windows Subsystem for Linux to do things here. Oh, let's see. There. See, I can switch to Windows Subsystem for Linux too. Windows Subsystem for Linux has its own version of GCC. See, it's much more recent. See, in Windows Subsystem for Linux, I've got version 9 of GCC. Okay, whereas on Windows, I'm using a fairly older version of GCC. Okay, so but it's the same compiler. You know, for what we're going to be doing with these simple threading examples, it doesn't really matter which GCC compiler we use. But since we're using the same compiler in Windows and Linux, we can kind of go back and forth between the two operating systems and see how things work. So I like using GCC on Windows because at least if you use Microsoft has its own compiler, you have to download it from them. You know, that the Visual Studio compiler, one trouble with it is it's massively huge. Okay, so it's a huge download and it's a fairly complex thing. And for a lot of times it's real overkill for what we need to do. So Windows Subsystem for Linux has a GCC compiler in it, and it's easy to put a GCC compiler on a Windows machine. It's just download this one zip file and you've got GCC. So I like being able to use the same compiler for both systems. Okay, so that's the C compiler. Okay, it's in this folder called MinGW. That's the name. If you Google MinGW, you'll see that it's a project for port. These are the people who took the GCC compiler and made it run on Windows. Okay, it's called MinGW because it's a minimal installation of GCC for Windows. But there's nothing minimal about it because 20 years ago when the project started, their goal was to get something running. So they called themselves MinGW. And then after a few years, they were no longer minimal, but they didn't want to change their name. So they kept the name MinGW, even though it's a full-blown complete version of GCC for Windows. But so everyone refers to it as MinGW. And currently there's a 64-bit version. The one we're using is actually an older 32-bit version. So you notice it's MinGW 32. So it's good enough for us to use the 32-bit version. If you download the current version, you get MinGW 64. Okay, so we're using the MinGW compiler on Windows, and it works pretty well. And it gives us a way of working that's similar to we can transition between Windows and Linux pretty easily this way. Okay, all right. Now, in this CS302 folder, there's also an editor in there. Okay, it's called Programmer's Notepad. And the idea is that what it is, I turn this editor into a little IDE for the GCC compiler. Okay, so let me show you what I mean by that. The editor is in this folder. The editor is actually that executable there. That's the editor. Okay. This is a shortcut to the editor. I'm going to take this shortcut and copy it to this pthreads folder. Okay. Now what I have now is I can use this editor to open these files, edit these files, and compile them. So for example, I'll drag this over to here. So there's my editor opening a C file, and under tools, I have a GCC tools. Now what the tools are is I put them there. See, if you go down here, if you click under tools options, you get this interface that lets you configure tools. You click on tools, you click on GCC, you click on edit, and I built a little tool here for compiling with GCC. Okay, so what this thing says is to go to the min.gw folder and use the GCC program in that min.gw. This is why you have to have everything on the same. This is why everything has to be on the C drive, because it's hard coded into this thing that everything is going to be on the C drive. Okay, but this is telling the editor is being told go to that folder and get a copy of GCC and compile what's in the window using these options. Okay, now watch what happens. So if I type tools GCC, see that file got compiled. It's that easy. Now it compiled it for Windows. See, it's a Windows program. See, it's a Windows program. The thing about min.gw is min.gw is the compiler from GCC, but it's been modified. I'm sorry, it's the compiler from from Linux, modified to produce Windows binaries. Okay, that's what the min.gw people did. If you just take the compiler out of Linux, it produces Linux binaries. So they modified the compiler to produce Windows binaries. So it compiles Windows and Linux programs both, but it compiles them to Windows binaries. Okay, so I can open any one of these files. Okay, and I can compile it. I can also run it from in here. See, I could run it by clicking on run. Okay, or I can just, if I want, I can just double click on the executable. Notice, but if I double click on the executable, it runs and disappears. Okay, notice that they run, they just, when they're done running, they disappear. So that's kind of the advantage to, if you execute it from here, this thing, the editor is smart enough to pop up a window, run your program in it, but then keep the window open. You can also go over here and open a command prompt and run the program from a command prompt. Okay, or and here's, I'll run the other program. Okay, see, I can run them from the command prompt too. Okay, so this is the system we'll use at the beginning of the semester. This is what we'll use. We'll use this GCC to compile these C programs. And again, all you have to do is download it from the website. Did it finally down? Oh, it finally downloaded. Okay, it did finally downloaded. Download it from the website. Unzip it. After you download the CS302 folder, when you download it, see, everything you need is inside of it. Just unzip it. Takes a little while to unzip it. You only have to do this one time. It might take a little while to download it if the network on campus is running kind of slow. And then you only need to download it once. Then you only need to unzip it once. Then after you've unzipped it, copy the whole folder to your C drive. And if you were in the operating systems class last semester, you probably have this already. Some of you were in the operating systems class last semester. This is the same compiler from the graduate operating systems class, and it's also the same compiler from the undergraduate operating systems class. It's a very nice, it's really nice to have a portable C compiler. It's really nice. If you're in a lab, if you're at work, if you're almost anywhere you are, you can actually just download this zip file, unzip it, and have a C compiler on any machine you're sitting at. You don't need any privileges, any special privileges to do this. This is one of the reasons why I like having a system like this, because it's portable, it's pretty convenient, and it works pretty well. See, okay, there's unzip. Now, the only thing left to do would be after unzipping it is cut this and paste it on in your C drive, and then you're good to go. And then after you paste it in the C drive, what I like to do is copy this shortcut to whatever folder you're working on. Actually, like I have a copy of it on my desktop here. See, I have a copy of it right on my desktop even. So you can copy that shortcut to whatever folder you want to work in, and then that shortcut will take you to that editor, and that editor knows how to talk to that compiler, and it all works pretty well. Okay. Oh, one thing it's missing, it used to have, see this folder here, Insight, is a Gooey Debugger, and it doesn't work under Windows 10. It used to work on Windows 7 and previous. So if you look in this, under tool, there is a debug tool. It probably doesn't work anymore. See, it's this is debugger. It doesn't work anymore. The debugger stopped working with Windows 10. Okay. At some point I might try to get this to, I might be able to find a way to fix it. Actually, no, this is a different debugger. This is the Eclipse debugger. This is the Eclipse standalone debugger, but also it's not working quite right either. Some point I'm gonna see if I can get these debuggers to work again. Okay, so this is the Eclipse debugger. That's not this one. That's a different debugger. I forget where that one's from. Okay, but that's the one thing that this little setup is missing a debugger. That's kind of the bad thing that it's missing. It used to have a debugger, and the debugger worked under Windows 7, and I used it for years. But then I was never quite able to get the debugger to work with Windows 10. And the people who wrote the debugger I was using had stopped improving it years before. It was an older debugger, and debuggers are more complicated than editors. So finding a good debugger is kind of tricky. And I did try. I tried using the Eclipse debugger, and that also didn't work real well. Let me see. Yeah, I'll see if maybe if I have some extra time, I'll try to get that debugger to work. It's kind of nice to have a debugger, but for this course, it doesn't really matter. We're going to be switching to Java pretty soon. We're not going to spend the whole semester working in C. The C is just to get us started with what is a thread. So for the most part, you're not going to be debugging code, because I'll give you code that hopefully has already been debugged, so you won't really need to be debugging anything. Okay, so let me clean up a little bit here. Okay, so I don't need this folder. I've already. And after you've unzipped this zip file, you don't need it anymore. So you don't need the zip files anymore after you've unzipped them. Okay. All right. So let's see. Now, first, let me stop. Does anybody have any question? I mean, if you're at home, you might be able to. You can follow along with all this stuff. You can try downloading that C compiler, downloading this code. Has anybody got any questions? Has anybody run into any problems? Anything not work, or anybody try anything that didn't work? Anybody got any questions so far? You definitely want to get threading is a tricky business. Threading is not a simple idea. So you want these programs to play around with. You'll want to be able to try them out and play with them. Okay. Well, let me show you another little trick here. You can compile these programs in the editor, but you don't have to compile them in an editor. You can compile them multiple ways. So let me just make sure get everybody used to this idea that you don't have to use an IDE. So for example, I can open a CMD at this. I can open a CMD here. Okay. Now, the compiler is, let's go back to it. If you installed it now, the compiler is in this folder here. See, C:/CS302 min-GW bin. There's the compiler. Well, I can, if I just type GCC here, Windows doesn't know about my version of GCC. But if I type C:/CS302/min-GW/bin/GCC, Windows knows about my GCC compiler now. So I can compile from the command line. Okay, so I can talk directly to the compiler. Okay, I know where the compiler is. I can just talk to it. So for example, now I'm in this folder and I've typed a path to the compiler, and I can tell the compiler that I want to compile the file 1A, and I want the output to look like .exe. Yeah, see, I just compiled it. Okay, yeah, I don't need an IDE. In the broader scheme of things, when you get job interviews and stuff, you'd be surprised. You can impress people more by not needing an IDE than you can sometimes by using an IDE, because there's a lot of people who don't know how to get around the command line, who don't know how to actually get things done on a command line. So, it's very useful to be able to do things from a command line. So you don't have to have the IDE all the time. Okay, so, and then I can just say delete. I can delete that. See, delete the binary file. Okay, so I can compile things from the command line, and also I put a make file in here. Okay, make files are files. If I okay, here's what a make file is: a file that directs the compiler. A make file tells the compiler how to make things. So I wrote a make file for this folder. Okay, and here's how you use the make file. Okay, well, actually, I'm sorry. It tells you in the first line of the make file tells you how to use it. To use this make file, you use this command here. So I'll just copy and paste that command. Now, what that's doing is, if I go back to the compiler, so I'm going to go back to navigate to the compiler, min-GW in the bin directory has a copy of make. They called it min-GW32 make for some bizarre reason. Like on Linux, it's just called make. The make program reads make files and makes things for you. Okay, this has been part of Linux since the very, very, very beginning of Unix. Make is 50 years old. Make is the traditional way. Like if you're going to build the Linux kernel, you use make to build the Linux kernel. Okay, and so make is a traditional way that people compile large numbers. You don't want to open 1,000 files in an IDE and then compile them one by one. You want to be able to just automate the process of compiling things. So make is the tool for automating the compiling of things. For some reason, the people who built min-GW, they called make min-GW32-make. I don't know why it's not just called make, but they didn't call this min-GW32 GCC, but they did for this one. Okay, now if I go over here and I tell Windows where to find make, okay, the make program looks for a make file in the current directory. If it finds a make file in the current directory, it executes that file. I have that file to have the compiler compile all these programs. So if I hit make, everything got compiled all at once. Okay, so the make program stepped through my make file and my make file told the make program to have the compiler compile everything. So I'm using the make program's reading a make file. The make file tells the make program to have the compiler program compile everything. So here's where the make file tells the make program where to find the compiler. And then here's the command that tells where the make file tells the make program to tell the GCC compiler to compile my files. Okay. So this is another way that you can build files. You can build them by having a make file. The make file is mainly so you can compile everything at once. Now, all these exe files need to be cleaned up. You clean them up by typing make clean. See, now all the exe files go away. Okay. Now, make clean is one of the things I have. It's actually a step in the make file. The make file actually has two parts to it. This part tells how to build the files. This part here says how to clean the files. They're just going to delete, it deletes all the exes. So this part here creates the exes. This one deletes the exes. Okay, now we're not going to talk about reading make files. If you're interested in learning about make files, this is something that's very, very, very useful to learn about. A little bit tricky to read. Notice that this is not easy to read. Make files are kind of inscrutable, but there are lots of documentation on the internet that explain how make files work. And if you end up working with C and C++ code on Linux machines, you'll use make files. If you work with C and C++ on Windows machines, most people tend to use Visual Studio projects, but there's problems with Visual Studio projects. First of all, you need Visual Studio, which historically is a commercial product you have to pay for. Make and GCC are free. They're open source pieces of code. But the Linux world tends to use Make. The Windows world tends to use Visual Studio projects. But there is a version of Make that comes with Visual Studio, because when you have to compile thousands of files, that's actually the big problem with Visual Studio projects. They're not usable with thousands of files. Okay, you cannot create a Visual Studio project that'll compile 10,000 files. The Linux kernel, for example, is thousands upon thousands of files that need to be compiled to compile the Linux kernel. So Visual Studio actually has a version of Make that comes with it, but it's not the Linux version of Make. It's a different version of Make, so you have to learn a whole new version of Make if you want to use the Make that comes with Visual Studio. But that's what Microsoft uses. When Microsoft builds their software, they don't actually use Visual Studio. They use the version of Make that they wrote for Visual Studio, because Make can compile large numbers of files much more manageably than Visual Studio projects can. Okay, so right now we have a whole bunch of ways of doing this. Okay, you can compile these things with the editor. You can compile with the command line. You can compile them with the make file. Okay. Okay. Now let's start talking about what's in these files. Let's start talking about threads. Okay. So let's talk a little bit about what is a thread. So far we've just been talking about getting this code to compile and things like that. So let's start talking about what is a thread. Okay. The heart of this is, let me actually the best way to explain threads is to draw a picture. I mean, if I had a blackboard, I would just draw a picture real quick. I can draw kind of a dumb picture here in Paint, maybe. Here's a computer. The computer is a CPU and memory. Okay, that's what a computer is. Now, in the computer is a program counter called a PC, the program counter. The program counter is a register inside the CPU. Okay. Now, what does the program counter do? The program counter holds an address that points somewhere into memory. Okay, the program is a counter that holds an address that points into memory. And what does the CPU do? The CPU, the most important thing you should know from architecture class is the CPU does fetch, decode, execute. Okay, what does that mean? The CPU takes the address that's in the program counter, goes over to memory, and reads that memory address, okay, and gets the data that's in the memory address, which is the CPU instruction. And it takes that CPU instruction and it takes it back over here to the CPU and puts it in what's called the instruction register. The IR, the instruction register. That's the fetch. Okay, fetch means get an instruction from memory and put it in the instruction register. So the program counter points to an address. The address is the address of a machine instruction. The CPU grabs that machine instruction to the instruction register. Now it's going to decode the instruction. Decode the instructions, figure out what it does. So for example, this instruction over here might be there might be an add instruction here, and then maybe right after it in memory, maybe there's some machine instructions, like after the add is suppose there's some instructions in memory. There's an add, maybe there's a move instruction followed by add instruction followed by another move instruction. Okay, just imagine there's 3 instructions. So what's the program counter going to do? It's going to get the move instruction, load it into here. That's the fetch. Then it decodes it, figures out, oh, it's a move. Then it executes it. It does whatever the move is. Then after it's finished that instruction, the program counter increments to the next instruction. So over here, this is a loop. After you execute, you go back up here and you do fetch again. So the CPU is in an infinite loop of fetch, decode, execute, fetch, decode, execute, fetch, decode, execute, right? So that's what it means to run a program. The CPU points at an instruction in your program, gets the instruction to the instruction register, decodes the instruction, executes it, then increments the program counter to the next instruction, and then does it again. Okay, so this is what we call single-threaded code. Okay, there's a CPU executing one thread of code in your program. Okay, now here's something that's a little bit tricky. Suppose I have more than one CPU. So suppose I have another CPU. Okay, so here's my CPU number 2. Okay, I'll make this one CPU. This is CPU 0. Okay, so I have CPU 0 and CPU 1. I have 2 CPUs. Okay, on my machine right now, if I bring up Task Manager, wrong one. See, I have on this machine 12 CPUs, numbers 0 through 12. Okay, so I have 12 CPUs on this machine here, numbers CPU 0 up through CPU 11. Okay, and if I go over here to performance, I look under CPU, there's my 12 CPUs. Oh, this one's, there's CPU 0, CPU 1, CPU 2. Okay, so I have multiple CPUs. All right. Okay, so each CPU has a program counter in it, and it has an instruction register. Okay, so each CPU has its own program counter. So this is the program counter of CPU 1. This is the instruction register of CPU 1. The thing is that this thing could be pointing right here. So this code here could be being executed simultaneously by more than one CPU. That's multi-threading. That's actually the heart of what we mean by multi-threading. I've got code in memory, one block of code in memory, and I have two CPUs with their program counters stepping through that code. Okay, so I can just keep, so however much memory I have over here, this is my program in memory. So this is the memory region that holds my program. Now my program, I'll make this, this is my program. Somebody else's program would be over here in memory. For example, this part of memory might be somebody else's program. Okay, I'll call this, this is program 1. And down here will be program 2. They could be both my programs, or they could be one is my program and one is somebody else's program. So for example, on this computer, I'm running, to go back to Task Manager, you see that I'm running hundreds of programs. Okay, each one of these programs is its own program in memory. You can see Windows regularly runs hundreds of them at a time. Okay, I have 12 CPUs. Now, what's interesting is I could have two CPUs running two different programs. So for example, one CPU could be running that program while the other CPU is running this program here. That's not multi-threading, that's multitasking. I have one CPU running one program and another CPU running another program. Okay, that's not multi-threading. So here's the so here's the memory of the other program. The other program is sitting in memory in these memory addresses. Okay, now it's the Windows scheduler that decides which CPU runs which program. Okay, and that's the operating systems book. If you go to the operating systems textbook, like if you go look at this book here, you see that after it talks about processes, it talks about scheduling. See, that's the very next chapter. After it introduces the idea of a process, it introduces the idea of scheduling. Scheduling is that the operating system decides, okay, which process do we point the CPU at? Do we point the CPU at this process? We point which CPU at which process? That's called scheduling. Multi-threading is when more than one CPU is allowed to be inside of the same process. Okay, so if I go back over here and put this CPU back in the other process, now if I put that CPU back in this process, if the scheduler says, okay, that CPU is in this process, then this is a multi-threaded program. So if there's two CPUs executing simultaneously in a program, then the program is called multi-threaded. Okay. Most modern operating systems are multi-threaded. They allow you to have more than one CPU executing at a time inside of a program. Okay, but you have to write special code to get that. Like if you just take a normal if you just write a Python program, you write a Java program, if you write a C program, you won't get multi-threading unless you do some special coding. So by default, a program only gets at most one CPU executing in it. That's the default behavior, that the program gets one CPU. That's the main method. The main method of your program is that one, what we call the main method of your program is actually sometimes referred to as the main thread. Your programs, when the operating system starts your program, it starts the CPU, it starts one CPU at main, and that's your one thread. Okay, so your Java program starts at main, that's its main thread. Your C program starts at main, and that's its main thread. Same with the Python program. Okay, so you get the one CPU that's pointed at your main method, and that's your original thread. If you want a second thread, you have to do something. And that's what we're going to start talking about. Like, what code do you write to get a second thread running in your one program? And we'll see that it's not a trivial matter to have more than one CPU running around in this code. It can introduce all kinds of problems, okay? And it can solve problems and introduce problems. Multi-threading has a lot of advantages and it has some disadvantages. So multi-threading solves some problems and creates other problems. Oh, let me save this before I lose this. I don't want to lose this picture. If I screw up, I'll delete it or something. Okay. So this is the you can describe this in words, but it's a lot easier to kind of draw a picture. And it's really helpful to actually visualize multi-threading as two CPUs with their program counters within the same program. Okay, like right now on this computer, I have hundreds of programs running. Okay, that means that if I were to look inside of memory, I'd have, my computer's also got, I think, 32 gigabytes of memory. All these programs are sitting in within my 32 gigabytes of memory. Like right now, my computer's using about half of its memory. Oh, my computer's got 16 gigabytes of memory. I'm using about half of it. Okay, that 8 gigabytes of memory, I'm using a little over 7 gigabytes of memory. That 7 gigabytes of memory is holding all these programs. But these programs actually also have multiple threads. Nowadays, here's a column that Task Manager lets me see how many threads a program has. So I'm going to turn on the threads column. Okay, there's the threads column. Notice that there's a program with 350 threads. There's another program with 183. Zoom, boy, that's weird. Zoom needs 183 threads. I can't begin to imagine what it's doing with 183 threads. Okay, Dropbox needs 150 threads. I wonder how many of them are spying on me. Okay, so that's weird. That's a lot of threads. Okay, and then some programs have 0 threads. That's a little bit weird. Oh no, I'm sorry. Nobody has 0 threads. So I was looking at the wrong column. Okay. The smallest number of threads of any of these programs is 1. You can't have less than 1 thread. Okay. If you write a simple program, we'll see when you write a C program, if you write a C program like you learn in C++, in the C class, the C++ class, it'll have 1 thread. Okay. And then there's some programs with 2 threads, 3 threads, 4 threads, and then they keep getting more and more, and then you get to these places where you have programs with hundreds of threads. I actually don't know what these things need. Why Zoom would need 183 threads? It's pretty rare to see a program. You know, there's a big jump. There's a huge number of programs in like the 20 to 30 threads is pretty common. Notice that there's a lot of programs in this range like that. And then at this point, you kind of start jumping up, and you go from 90 to 150 to 180 to 350. Oh, 350, that's the operating system. So that's maybe not surprising. See, that process called system really is the operating system. So it's maybe not so surprising that there'd be a large number of threads in it. Okay. Notice that Chrome doesn't even need that many threads. Each Chrome process is in a medium number of threads, around 15 threads Chrome process. Okay. Okay. So now what's interesting is that you could have now, oh, here's something that's important. I don't have 350 CPUs. I don't even have 90 CPUs. I don't even have 28 CPUs. How can this program have 28 threads? Okay, how can Chrome have 17 threads? Okay, I only have 12 CPUs. One of the things that when you, this is what's covered a lot in the operating systems class. You can suspend when the CPU is executing in here. The CPU, suppose I only, let's go to another extreme. Okay, let me make a copy of this picture. I'm going to do multi-threading with one CPU. Okay, see, to make things easier, I said, imagine there being two CPUs, but there doesn't have to be two CPUs. To do multi-threading, I don't need two CPUs. So let me get rid of one of the CPUs, and then I'll talk about multi-threading with only one CPU, because you can still do multi-threading even if you only have one CPU. So let's get rid of, whoops, get rid of one CPU. Now, this is one of the basic ideas of operating systems, because, multi-threading existed long before there were multi-core CPUs. So the idea of multi-threading is old. Multi-core CPUs are only like about 10. Multi-core CPUs came out around 2005, I think is when they first came out with them. So multi-core threads are much more recent than the idea of multi-threading. Okay. So now I've got one CPU, but I want to do multi-threading. Okay, so here's what I do. There's an idea, there's another concept that's a big part of operating system, is that there's there's a data structure that's part of the operating system called a thread control block. Okay, so I'm going to draw several thread control blocks. Each thread control block is a data structure. So these are going to be multiple instances of the thread control block data structure. So this is a thread control block and another thread control block. So you have to imagine these as instances of a data structure. Okay. Now what I'm going to do is I'm going to have 3 thread control blocks for the read process. So I'll bundle these together. These are 3 thread control blocks for program 1. Okay, and I'll have a thread control block for program 2. I'll give program 2 a thread control block. Program 2 is going to get one thread control block. Now, what this means is this program 1 has 3 threads. Program 1 has 3 threads. But program 2 only has 1 thread. There's only one CPU, but I have 4 threads. 3 threads in program 1, and I'll have has 1 thread. Okay. So program 1 has 3 threads. Program 2 has 1 thread. What that means is program 1 has 3 thread control blocks, and program 2 has 1 thread control block. The thread control blocks belong to the operating system. And here's what happens. There's only one CPU. the CPU is going to be shared between all the processes and threads. Okay, so here's what happens. The CPU has got a bunch of data in it. When I want to stop running one thread and go to another thread, what happens is we have to do what's called a context switch. The operating system will stop the CPU, take all the data in the CPU, transfer it to a thread control block data structure. Then it'll take all the data from the other thread control block data structure, move it into the CPU, and restart the CPU. That starts a different thread because there'll be a different program counter. So for example, the program counters are in the thread control block. So I'm running out of room here, but a copy of the program counter is in the thread control block. Okay. So there's a copy of the program counter in the thread control block. Now, what that means is when it's time for this thread to stop running on the CPU and some other thread to start running on the CPU, the operating system takes this program counter, moves it into there, and then takes the program counter from here, moves it into here, which jumps the CPU to some other part of this program and lets another thread run. Now, at some point, the operating system might switch to this thread control block. When it switches to this thread control block, it's actually running a different program. Okay. By having 3 thread control blocks tied to this one program, this program can have 3 threads, even though there's only one CPU. Okay. And in total, I can have 4 threads, even though there's only one CPU. Now, what's happening over here in Windows is that's exactly what they're doing. A process can have 26 threads, even though there's only 12 CPUs. What that means is that process has 26 thread control blocks. So that's exactly what that means. The process has 26 thread control blocks. The CPUs, the 12 CPUs, are cycling between all these thread control blocks. Right now, there's a total of about 1,000 thread control blocks. If you add up all these threads, this machine right now, oh, actually, let's see. Someplace someplace Windows will tell me exactly how many threads are running in total. I can't remember where that is. It's not here. Here it shows me how many threads each process has. There's some place where if I don't remember where it is. There's some place where it'll tell you the total number of threads. Oh, here it is, 3,200 threads. Okay. Right now, there's 3,200 threads. What there really are is 3,200 thread control blocks, 12 executing threads. There's only 12 threads that can be running at a time. There's only 12 of these CPUs, but there's 3,000 of these thread control blocks. And the operating system is picking a thread control block, moving the data from the thread control block into a CPU, which makes the CPU execute a thread for a little while. The little while is usually on the order of like about 50 milliseconds. That's called a time slice. Okay, the time slice is the amount of time the operating system lets the CPU run one thread. And if you go to this textbook here, that's part of this chapter on scheduling. Okay, in the chapter on scheduling, it talks about this idea of switching the CPU between these threads and processes. Okay. Right. So I can have one CPU and have multiple threads, and I can have multiple CPUs and have only one thread. Okay. A modern computer will have multiple CPUs, and most of the processes will have multiple threads. Though some processes, we saw here, some processes still will only have one thread. Okay. Some processes will still have only one thread. Okay. Now, let's write a little baby program real quick. Okay, write a baby program .c. Okay, a baby C program. A baby C program with C. I'll make it like here. It's going to be int main doesn't take any parameters. I'll just do while one. Let's see, what's the simplest thing I could do in an infinite loop? I could print something. Okay. And if I'm going to print something, I need to include okay, this should compile. Okay, there's my baby C program. Okay. This program, if I run it, it's just printing X's. Now go look in Task Manager for it. There's my baby C program. And here's interesting. It's got 2 threads. I actually don't know where that extra thread is coming from. I don't know why that program's got 2 threads. You know, let's get rid of the printf. I think it might have to do with the printf. So let's make this program not even do printing. Let's make it even simpler. The printf might be Windows. Modern operating systems are getting really complicated. A few years ago, this baby program would have had only 1 thread. It definitely would have. I remember, but now it's kind of funny that a baby program like this can still have more than 1 thread. And I think it might be because of the printf and because of the console. So let's try, see, what would be something even simpler than printing? Let's just increment a variable. Okay. So let's see. Okay. Now the program just sits there. Okay. Let's look for it in Task Manager. Still got 2 threads. I actually don't know what that second thread is. I have to figure out where that thread comes, because by everything I know about the C language, there is only 1 thread in a C program. Does anybody have any idea? Has anybody ever seen it? Anybody have a clue what might be the other thread? Oh,
could it be the command window?
No, look, it went away. It was some temporary thread. Yeah, that's what I was thinking too, that it may have something to do with the command window. I had the same thing. In the back of my head, I wondered if maybe the other thread had something to do with the GUI window. But the thread went away. Look, see, it's gone now. Now I'm down to 1 thread. Maybe it has something to do with initializing memory. It might have been a thread that was started, it was there temporarily. Let's kill the program and start it up again. Okay, it's got 2 threads. Let's wait a little while, see if the same thing happens, see if one of the threads goes away. Oh, I think it will. Now, yeah, finally, one of the threads went away. I'm not sure what it was. Now let's go back to the GUI version. Let's see let's be a little bit patient on the GUI version and see if one of the threads goes away then too. Okay, so okay, so here's the version that was. Okay. No, it's Let's see if this, one of the threads goes away this time too. If we wait long enough, maybe it might have been a thread that was initializing memory or doing something to get the program going. But the program only, as far as I know, has officially one thread. I'll have to see if I can dig through any literature that might explain where that other temporary thread is. Let's see if this one goes away too. It might have to do though with the console one. Oh no, it went away. There's down to one thread. And that thread is the main method. That's the main thread. I wonder what that other thread is. Okay. Okay. So simple programs in theory, a main method is one thread. When you start a C program, the C program starts at main, and that's the CPU will be pointed at your main method. You know, you have to, it's pointed at the address that the main method is loaded to after it's been compiled and assembled. Okay, so the program counter will start pointing at main, and then it'll just cycle through this little loop. Okay, all right. Now let's start looking at the code that will, what would allow us to get more than one thread in a program? How do you get Windows to give you another thread control block? Now, you don't actually get thread control blocks. You don't ask the Windows for thread control blocks. Thread control blocks belong to the operating system. They're an operating system idea, but they are the idea. That's how the operating system maintains the bookkeeping for this. The operating system keeps track of all the threads by constructing thread control blocks for each thread. For example, you could if you Google thread control block, you'll see that it's got a Wikipedia page, a data structure in the operating system kernel. Okay, so see here, here's the information that's contained in a thread control block. See program counter. See, that's what we were saying. That's the main idea. What's in the thread control block is the program counter. Keeps track of the current program instruction in the thread. Okay. So that's the main thing about the thread control block. It keeps track of where the CPU is, and then the CPU essentially gets frozen. One way people think about it is when the CPU is moved into the thread control block, you think of the CPU as being frozen in time. So for a while, the CPU is not doing. Now that's not true because the CPU picks up another thread control block. But from the point of view of this program, it's like this program freezes while it loses the CPU. And then when the CPU gets back to this program, it just picks up right where it left off. Okay, so by storing the program counter in the thread control block, you can remember where the CPU was at that point in the program. It's just sort of like the same thing you would do if you were doing some task and you had to be interrupted. You might write a note to yourself about where you were in the task, so that when you went back to the task, you could pick up, you could read your note and say, oh, here's where I pick up. The thread control block is where the operating system makes a note to itself about what the CPU is doing when it interrupted this program. And then when this operating system decides that the CPU should go back to that program, it goes to the thread control block to figure out where it was. But the program can have any number of thread control blocks. Oh, here's an interesting thing. If I have 12 CPUs, let's go back to. So for example, this Chrome process has got 16 threads. Could all 12 of my CPUs be executing in that one process? The answer is yes, but probably not. If the Windows operating system, for some reason, thought that that would be a good use of the CPUs was to put them all in this one process, it could. More than likely, the CPUs are just kind of being spread around evenly throughout all the processes, but part of the scheduling of the operating system is the operating system gets to decide on its own by various algorithms which threads should get which CPUs. So it's entirely possible that all the threads, all the CPUs could be executing those threads, but it's not very likely. Yeah. At any given instant of time, you can't ask what threads the CPUs are running because they're switching incredibly fast. The CPUs run a thread for about 50 milliseconds. Now, at 50 milliseconds, you execute millions of instructions. Remember, on a modern computer, you execute instruction in about a billionth of a second. So for 50 milliseconds, you're going to execute thousands of instructions. But that's a very brief amount of time to be spending a CPU on. So the CPUs are switching between these thread control blocks very quickly. You know, they switch from one thread control block to another about every 50 milliseconds. Okay? And that makes your computer look like it's really working. You know, oh, like over here, my program appears to be running nonstop, but it's not running nonstop. It runs for 50 milliseconds, then it has to wait its turn to run for another 50 milliseconds. It's only got one thread, okay? And it has to, you know, those threads are being moved, the CPUs are being moved around all these processes, but this program gets enough attention from the CPU that appears to be running continuously. You know, same true with my editor. My editor, you know, as I'm typing, the editor is really not running all the time. The editor is running for 50 milliseconds, then pausing for a little while, then running for 50 milliseconds. But that's happening so quickly that from my point of view, the editor is just always responding to me, but it's not really always responding to me. So that's the whole multitasking aspect of the operating system. Okay. All right. So we run out of time now. So what we'll do on Wednesday is start looking at the code in this folder that actually creates the threads. Just show you real quick. It's this. I'm sorry, I opened the wrong file. See this function, create thread, p thread create. We're going to see. You'll read the readings for the book for the course. And you'll see that that's the heart of it. That is the function that you call to tell the operating system to create a new thread control block for your program. Create thread is what creates new thread control blocks. Okay, so that's where we'll start. We'll start talking about this idea of calling a function to tell the operating system that you want your process to get another thread control block so that your process can have more than one CPU executing in it. Okay, anybody got any last minute question? Any question about what we're talking about? Or okay, so yeah.
Yeah, a quick question, like this multitasking or multi-threading is happening in user mode or it goes to kernel mode too?
Well, it happens in, the answer is both. The actual switching from one thread control block to the other happens in kernel mode. But your threads are running in user mode. So your threads run in user mode. So this CPU is executing my program in user mode. But every 50 milliseconds, the CPU is switched to kernel mode. The CPU decides what thread control block to switch to. Then the kernel returns to user mode in the other thread control block. So the switch from one thread control block to another is done in kernel mode, but my threads are run in user mode. But
Okay. So there is a system call each time when they are changing the
an interrupt,
blocks.
not a system call, an interrupt. There's an interrupt.
Okay.
Yeah, and what it is, I can show you real quick. There's another little piece to this picture. There is a little box over here called the timer. The timer fires every 50 milliseconds. And what the timer does is the timer generates an interrupt that goes to the CPU. That's the thing that switches the CPU from user mode to kernel mode. This interrupt, so this is an interrupt. The interrupt comes in and that forces the CPU into kernel mode. So it's not a system call, it's an interrupt. It's actually a hardware interrupt. It's a built-in hardware interrupt that's part of the motherboard. The timer is part of the motherboard. The timer is connected to the CPU, and every 50 milliseconds, it tells the CPU, time. It's like somebody taps you on the back every 50 milliseconds and tells you it's time to switch to do something else. Okay, so this interrupt switches the CPU from user mode to kernel mode. When it's in kernel mode, it picks a new thread control block. Then it returns control back to the CPU in user mode. Okay.
Okay, thank you.
Okay, so we'll quit there. And like I say, we'll start looking at the code examples on Thursday. Okay, so I'm going to stop sharing and I'll stop sharing and I'll put a copy of this video up on YouTube after class. It'll get up there in about an hour or so. It'll be up there. Okay. Let's see. Let me find I lost my mouse. Okay. So bye-bye. See you in a couple days.